Hello and welcome back. Today, let's dive into the concept of physical significance of electric field, field lines, and electric flux. So far, we've defined the electric field and learned how to calculate it. But today, let's go a step further and answer a deeper question. What does the electric field actually mean? What is its physical significance? The electric field isn't just a mathematical quantity. It's a real, measurable, physical phenomenon. Whenever there's a charged object, it creates an influence, a kind of invisible force field around it. This field has the power to act on any other charge placed within it, even across a distance with no physical contact. So, the physical significance of electric field is this. It describes the ability of a charged object to influence the space around it and exert forces on other charges that enter that space. Just like a magnet creates a magnetic field around it, but charge creates an electric field, and this field stores energy, exerts force, and determines how charges will move. Now, how do we visualize something invisible, like an electric field? That's where the concept of electric field lines comes in. Electric field lines are imaginary lines that we draw to represent the direction and strength of an electric field in space. They help us see what's otherwise invisible. Each point on a field line shows the direction of the electric field at that point, which is the direction a small positive test charge would move if placed there. Let's now understand the basic features of these lines. Here are the key properties of electric field lines you must remember. They begin on positive charges and end on negative charges. If there's only one type of charge, the lines go to or from infinity. They never intersect. Why? Because if they did, a single point in space would have two directions of electric field, which is impossible. The density of lines represents field strength. More lines in a region equals stronger field. Fewer lines equals weaker field. Field lines are always perpendicular to the surface of a conductor. This reflects the fact that electrostatic equilibrium means no tangential field on a conductor's surface. In uniform fields, like between parallel plates, field lines are parallel and equally spaced. So, electric field lines help us visualize the invisible and understand field strength, direction, and symmetry. Now that we can see electric fields using field lines, the next step is to measure how much field passes through a given surface. This brings us to the concept of electric flux. Electric flux is defined as the total number of electric field lines passing normally through a surface. Mathematically, electric flux phi is given by phi equals E dot A equals E multiplied by A multiplied by cosine theta, where E stands for the electric field strength. A stands for the area through which the field is passing. Theta is the angle between the electric field direction and the normal perpendicular to the surface. Cosine theta means we take the cosine of the angle between the field and the area vector. The SI unit of electric flux is Newton meters squared per coulomb. So, what does this mean practically? If the electric field is perpendicular to the surface, the flux is maximum. If the field is parallel to the surface, no lines pass through, and the flux is zero. If the surface is curved, we calculate the flux in small parts and integrate over the entire surface. Why is flux important? Because it helps us apply Gauss's law, which relates the net electric flux through a closed surface to the charge enclosed inside. Electric flux gives us a tool to connect field lines to physical charge distributions. Also, it helps us understand shielding, field distribution over conductors, and energy flow in electric fields. So in short, electric field defines how a charge influences space. Field lines help us picture that influence. Electric flux measures how much of that influence passes through a surface. Let's recap what we've covered. The electric field is a real physical entity representing the force per unit charge. Electric field lines are imaginary lines that show the direction and strength of the field. Electric flux measures how much field passes through a surface, helping us bridge the gap between fields and enclosed charges.